In this video, we're going to talk about some of the ideas in Chapter 2. This should not replace you working through Chapter 2 on your own, and it should not replace you doing practice problems in my math lab. Chapter 2 is review of a lot of other math courses. If you took Math for Liberal Arts or a similar class, this should probably be familiar to you. If you remember algebra from high school, this should probably be familiar. So the first part of Chapter 2 talks about graphing. So let's just review some things about graphs. We always refer to points on a graph in terms of first the x coordinate and then the y coordinate. It's always x comma y. The x-axis is the horizontal axis of the graph. It is the line that proceeds from left to right. The y-axis of a graph is called the vertical axis, and it goes from the bottom of the page to the top of the page. If you graph by hand, make sure you label both your x-axis and your y-axis, and make sure you have an arrowhead on them. By tradition, graphs are divided into 4 quadrants, as you see here. Those quadrants are always named with Roman numerals: quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So one thing you'll have to be able to do is to plot points on a graph. You may, in homework, have to know what quadrant a point is in. So for example, the point -2 comma 4 here is in quadrant 2. The point -5 comma 0 is not in a quadrant. Instead, we say it lies on the x-axis. Finally, the origin has the coordinates 0 comma 0. It's the point where the x and the y-axis intersect. So there are different ways we can sketch graphs. Most of what we do in this class will involve only linear functions. Your textbook talks about other functions. They talk about quadratics and they talk about polynomial functions. That is beyond the scope of finite math as it is taught here. You are free, of course, to take a look at that information on your own. I would encourage you, in fact, especially if you're transferring on to a college that requires finite math. And I know some schools have different requirements for the course. A big part of it is some places college algebra is a prerequisite for finite math, and in other places it isn't. So different versions of finite look different. All that is just to say that what we're going to work with primarily in this course, not entirely, but mostly, are linear functions. In other words, functions that are straight lines. So when we sketch the graph of y equals -2x plus 5, there are different ways we can sketch it. Remember that because it's linear, we're going to have a straight line. And a straight line, as you know, has an infinite number of points. So we don't have time to graph an infinite number of points. So what we do instead, one approach, is to make a table like this. So we take x values that are easy to graph or easy to work with. You always want an x value that is negative. You always want to use 0 as an x value, and you always want an x value that is positive. The problem will sometimes tell you how many x values you need to choose. You need always a minimum of 3. Often you're going to use 5. It's going to give you a better looking graph. So what we did here, for example, is when x is -1, we just plug -1 into the other side of this equation, and we get our result. So if x is -1, -2 times -1 is +2, +2 plus 5 is 7. So when x is -1, y is 7. And that's the point we see plotted near the top of the graph. It doesn't matter what specific points you use, as long as one is negative, as long as one is 0, and as long as one is positive. You can do something similar when you have to graph something that will be a different shape. So this is the graph of a parabola. This would be the graph of a quadratic equation. A quadratic equation would have one of the variables, the x variable is going to be squared. So you have, this would be x squared -4 or something like that. There too, you're going to have several points. You need at least 3. Here it's a little trickier because you want to make sure you have enough points that you recognize it's a parabola. You should recognize it's a parabola when you see that something is being squared, but you need more points when you're graphing a parabola, typically. So here's the points plotted, and then here is a smooth curve that is connecting those points. Again, certainly in the final exam for this course, you don't have to worry about quadratic functions or quadratic graphs, graphing something like this. You will see a problem or two like this in the homework and on the quizzes. This is a similar type of graph you aren't going to have to worry about in your future in this course. But it might show up in the homework occasionally, or on a quiz, I suppose, as well. So it's the same idea. You're going to plug x and y values in and then plot it. And you'd recognize here that the y values will never be less than 0. This is the graph of a square root function. We can solve an equation by graphing it. The solutions of a graph, or the solutions of an equation when we graph it, are the x-intercepts of that graph. So wherever the equation crosses the x-axis, those are the solutions for any equation with one variable. You will also have to read graphs at times. So here is an example of the S&P 500 index value. And so you might have to estimate what is the index value on day 10, what is the difference between day 14 and day 20, and stuff like that. Revenue functions and cost functions are going to be important in this course. They are going to show up again, including in the final exam. And so you need to be able to work with them a little bit. This is going to be a more complicated one than you'll have to work with because these aren't straight lines. These are curved lines. Just remember for right now, a revenue function represents how much income a business is making. And a cost function is how much it costs them to stay in business. When the revenue and the cost function intersect, that's the break-even point. This particular graph has two break-even points where cost equals revenue. For what you're going to have to do eventually in the final exam, there is a single break-even point because it is a linear function. It is not a kind of a funky one like this one is. You can use your calculator to graph functions. One thing that people struggle with the calculator is using the window function, and let me actually pull up the calculator to show you that. When you hit the window key, you're going to see a screen that looks something like this. You don't have to worry about the bottom values of the screen. Here's what you have to worry about. X-min and X-max. These are how much of the x-axis will be shown. The x-axis goes on forever in both directions. And your calculator can handle a good chunk of that. Usually the default is going to be -10 to +10, and that will work for some types of graphs and it won't for others. If we're dealing with the number of units that a business produces, say, how many cell phones is a business making? And it could be from 0 cell phones to, we'll say this is in millions, to 50 million cell phones. And so the next one, X scale, and some calculators will give you what it means, some versions of the TI-84. This is the distance between the tick marks. So if we put 1, that's going to be way too many tick marks. Let's instead put 10. So every 10, there'll be a tick mark. There'll be a tick mark at 10, a tick mark at 20, a tick mark at 30, a tick mark of 40, a tick mark of 50. So X is how many is produced, and Y is going to be our revenue from producing them. So we aren't going to have negative revenue. We might have negative profit, but we are going to make at least $0. So that's going to be our minimum for Y. And let's say we might make up to, I don't know, $3 million. So we're going to have from $0 to $3 million. So here, for Y scale, we want a lot of tick marks. We want maybe a similar number of tick marks. So we won't do 10 though. We'll do a multiple of 3 so we can sort of get in here. We'll do 12. I think that will look good. Don't worry about res or change in X or trace step for our purposes in this class. And so what this means then is when I go to graph something and I have a value in here, let me see what, I think I have a value in here, what I should have fixed before. This is the distance between tick marks. And since I'm only going up to 3 here, I want my distance to be a decimal. So my distance is a quarter of a unit between each one. So now when I go to graph, I see my function, the graph my function. So here are my x values of 10, 20, 30, 40, 50. Here are my y values of 0.25, 0.50, 0.75, 1, 1.25, 1.5, 1.752, and so on. So using the window function, we can manually determine how to make sure something will show up in our calculator if we want to graph an equation on our calculator. We can also use the zoom key, and some of these are built in to have some things that usually work. Zoom standard will often work if we want a sort of a traditional graph with axis 1, 2, 3, and 4. If you go on and take statistics, zoom stat works for some types of statistics things. This is going to look similar to the other, but sometimes there's some changes there. So window gives you very precise controls, and then zoom and these different ones gives you sort of default ones. So that's very useful when you are making changes there in your calculator. So the next several slides, if you're going through this on your own, the PowerPoint online, are just different examples of graphs on the calculator and looking at different windows. I would encourage you to use your calculator for graphing. There are tools in my math lab for graphing that you'll do for some of the assignments. The tools are very intuitive. They are far easier than doing it by hand. The calculator is also far easier than doing it by hand. Section 2.2 is equations of lines. This again is something that comes from algebra in high school that is reviewed a little bit in math for liberal arts that people sometimes forget about. So first we have slope. Remember, the slope is the change. You take 2 points of a line, on a line, doesn't matter what, it could be any 2 points, and it's the change in the y value divided by the change in the x value. Change in y divided by change in x, or rise over run. So here we have y values of 6 and -7. And we have x values of -5 and 4. So -7 minus 6 is -13. 4 minus -5 is +9. So our slope is -13/9 for this particular graph. So to find slope, whether you're using a graph or you're just given the points, you just plug that into the formula. Change in y over change in x. Remember that whichever point you start with for y, you have to start with the same point for x. That's the #1 mistake that people make. Remember that every horizontal line, like this, has slope of 0. Every vertical line, like this, has an undefined slope. Horizontal line, slope is 0. Vertical line, undefined slope. If a line is moving towards the upper right of a page, we say it has positive slope. So this line has positive slope. If instead we had a line that was moving towards the bottom right of the page, like the one I just drew on here, that would have negative slope. If a line has slope m and the y-intercept, the point where it crosses the y-axis of b, then it's the graph of the equation y equals mx plus b. This is called the slope-intercept form of an equation, and it's a form you have to be familiar with. If you see something that says y equals k, where k is some number, like y equals 3, or y equals 12, or y equals -2.5, then that is a horizontal line whose y-intercept is k. Any two lines that are not vertical are parallel if they have the same slope. Any two non-vertical lines are perpendicular if the product of their slopes is -1. So here we have two lines. They both have slope -2/3. They are parallel. Here we have one line whose slope is -1/3 and one line whose slope is +3. Negative 1/3 times positive 3 is negative 1. So we know these two lines are perpendicular. Point slope form is a line has slope m and it passes through a point x sub 1 comma y sub 1. Then if we have y minus y sub 1, the y coordinate of that point, equals the slope times x minus x sub 1, the x coordinate of that point. That is called the point slope form of the equation of the line. So 2x plus y equals 2x plus 1 would be slope intercept form. We could rewrite this into point slope form. I'm going to get a text box here because it's hard to draw on my computer here. So point slope form. So we're going to look at what point this goes through. We know what slope is, so we know that m equals 2. It goes through the point 1 comma 3. That's this point right here, 1 comma 3. So we have y, that is in white, and you can't see it, it looks like to me. Try it again. We have y minus the y coordinate. It should be a lowercase y. Y minus the y coordinate equals the slope times the quantity of x minus the x coordinate. This is in point slope form. If we do all our math, we distribute everything, we would wind up with 2x plus 1. So y equals 2x plus 1 is slope intercept form. Y minus 3 equals 2 times x minus 1 is point slope form. All right, so we have point slope form up here. And down here we have slope intercept form. Here we have another example of slope intercept form. The other thing you need to be able to do is determine what's what here. So the slope of this line is negative 3. So again, we are going to say here that m is always what we call slope. M, and it's always a lowercase m, is negative 3. It's not negative 3x, it's the coefficient of x. And then b, so if we're actually talking about the point of the y-intercept, we would write the point as 0 comma negative 11. But if we're talking about what plugs into b, it's just the y coordinate of that, which is negative 11. So that's our y-intercept. Again, since we know what slope is for this line too, we could write this in point slope form by plugging in negative 3 for slope and by plugging in these coordinates right here, which are negative 4 comma 1 for x sub 1 and y sub 1. If k is some constant, in other words, it's a number, not a variable, then the graph x equals k, like x equals 2 or x equals negative 5 or x equals 43, is a vertical line that has x-intercept of k. So these are the forms you should be aware of. The other one we haven't talked about in this presentation is general form, which is ax plus by equals c. You'll use that when you find x and y intercepts, which is something else you need to be able to do. Here we have an example of where slope is a decimal. This is slope of 0.76x. Here we have a large slope. Slope is 453. So be able to find slope, be able to work with those different formats of lines. 2.3 and 2.4 both involve linear, or 2.3 rather involves linear models. So a linear model means it's roughly in a straight line. This isn't perfectly straight, but it's roughly straight. And so this means that as x increases, y tends to increase. We could also have an example where x increases and y tends to decrease. Those are linear models. From this, we can form what's called the line of best fit. The line of best fit may, like here, include some of the points. There are ways in statistics courses where we learn other ways to do lines of best fit. We are going to about linear inequalities. We're going to come back to these in a later chapter with two variables. Here we're just looking at one variable ones. If you took math for liberal arts, you learned this there as well. Inequalities could be greater than or less than or greater than or equal to or less than or equal to. Remember, if you're solving linear equalities, it's like solving an equation. You're trying to get the variable on one side, the constant on the other. And remember, for linear inequalities, when you multiply or divide by a negative number, the sign changes. It's only if you multiply or divide by a negative number. If you multiply or divide by a positive number, the sign does not change. And if you add or subtract a negative number, the sign does not change. When I say it changes, I mean it changes direction. If it was less than, it becomes greater than. If it was greater than, it becomes less than. This is how your textbook handles graphs of these things. This is a little different than you might have learned in Math for Liberal Arts, where you might be used to using open circles or filled circles. Your textbook instead uses interval notation, which involves a parentheses like these if it were an open circle. So this would be the inequality that negative 7/3 is less than x is less than 5. Or negative 5 is less than x is less than 5. Or this one that's a little more complicated than we did in Math for Liberal Arts. This is, we go from negative infinity to negative 5, but not quite negative 5, and then greater than 5 up to infinity. Your textbook examples for linear inequalities use parentheses here. And I don't know why they only use those examples. If it is included in the answer, if it's greater than or equal to, if equal to is part of, then we use a bracket instead of a parentheses. And so as you're reading through chapter 2.4, if you looked, for example, at example number 2 on page 96, you would see an example of a bracket being used instead of a parentheses. And a bracket is what we would use a filled circle with in some other math courses. So these are some of the things that some of the main ideas of chapter 2. We are not covering 2.5, and we are not, we're not covering 2.5 specifically. You can go on and look at that, of course, if you want, but it's not required. If you have questions, please let me know.